So in this video, we're going to discuss the kinematics of angular motion. We'll look at the relationship between angular and linear kinematics, introduce you to the concept of the kinematic sequence, as well as centripetal acceleration. So when we're describing angular motion, we need a frame of reference, specifically a rotational frame of reference. And what I have here is a Cartesian coordinate system that's not any different from the coordinate system that we use for linear motion. The only thing that we need to emphasize here is that when we're talking about rotation, it occurs about an axis of rotation that is perpendicular to a plane in which that motion occurs. So for example, if a motion occurs in the xy plane, the rotation would occur about the z-axis because it's perpendicular to it. Likewise, the x-axis is perpendicular to the plane defined by y and z, and the y-axis here is perpendicular to the plane defined by x and z. Now, that gets a little bit confusing because of a Cartesian coordinate system such as that, xyz is relatively arbitrary. So let's look at it in clinical planes of motion. The frontal plane, for example. The axis perpendicular to the frontal plane is the AP axis, the anterior-posterior axis. In the sagittal plane, it's the medial-lateral axis, and in the transverse plane, it's the superior-inferior axis. Okay, so everything in terms of measuring, in terms of kinematics, when we make these measurements, is with respect to a rotational frame of reference. So what is angular kinematics? So, well, if you're familiar with linear kinematics, it's not that much different. You know, we're still talking about displacement, we're talking about velocity and acceleration. These definitions are pretty much the same. The only difference now is our rotational frame of reference and the way that we measure and evaluate angular motion. So this is, for example, such as the angular position or angular displacement, which can involve that degree of movement that can be measured in degrees as well as in radians, as well as the radius, which is the distance from some given point on that circular path and the axis of rotation. So, as I mentioned earlier, the basic concepts are still the same in angular kinematics as they are with linear kinematics, except where we have a specified axis of rotation. The force that is applied to cause that rotation, if you guys remember, that's called a torque. That force is applied at a perpendicular distance away from the axis of rotation, otherwise known as a moment arm. You should know that. The segment rotating around an axis may have the ability to travel completely in a circle, that's pure rotation or revolution, or it may have some combination of angular as well as linear motion. So, as with linear kinematics, our first concern that we have with angular motion is angular position, or the starting position. That is simply the angle between two lines or two vectors, or I'm going to show you in a second, between a local axis or a locally defined axis and a reference axis. So for example here, let's just say I wanted to measure that angle in the red, that line, with respect to the horizontal axis, or the x-axis in this case. There are a couple different examples of how this angular position is measured. In the body, for example, there's the absolute angle, the absolute angle, which is measured with respect to a fixed reference frame, such as the global reference frame, or otherwise known as the global coordinate system, or the room, or the lab. Whereas a relative angle is one in which that angle is measured with respect to a moving frame, a moving coordinate system. So I give you a couple examples. For the absolute angle, the pelvis is typically measured with respect to the room, or respect to the lab's coordinate system. Whereas the other joints, such as the shoulder, the knee, the elbow, the ankle joints, are all relative angles. Take, for example, the knee. That is the angle between the tibia and the femur, or the hip. That's the angle between the femur, or the angles of rotation with respect to the pelvis. Remember, 3 dimensions, so you can measure hip flexion, extension, abduction, adduction, internal and external rotation. You can only measure that with respect to its, usually it's the adjacent proximal segment. So anyway, that's relative angle, whereas pelvis is an absolute angle because that's measured to the room or to the lab. So here's an example, is hip flexion, for example, is measured with respect to the pelvis, and that is hip flexion extension. For the knee, that is the tibia with respect to the femur, or more specifically, that is the tibia measured with respect to the coordinate system that's defined at the femur. We call it a femoral coordinate system or a local coordinate system for the femur. We could do the same thing for the shoulder, for the elbow, even for the trunk. Typically, trunk is measured with respect to the pelvis. So the change in angular position is otherwise known as angular displacement. It's the same thing that we discussed in linear kinematics. Again, this time we're talking about a change in angular position, which is either in degrees or radians. I'll talk about the difference between the two. And obviously a characteristic of the circular motion that's important to note is the radius, right? The distance between the axis of rotation and the given point or the line of action of a force that causes a torque. So how can we convert from degrees to radians, and why is that important? Well, it turns out that the ratio between the circumference of the circle and the diameter of that circle is given by a mathematical constant known as pi, as I've shown you here. I think most of you know what pi is about if you've taken math or even high school math. And you can memorize the first 8 digits of pi, 3.141592, by memorizing this moniker. May I have a small container of coffee? You only really need 6 or 7 digits. You actually really only need maybe 3 digits in order to calculate these angular motion or angular kinematics. But it turns out that the Guinness World Record for for reciting the number of digits in pi is 67,890 by Lu Chao of China. This is back in 2005, and I believe still holds it. I don't know why anybody would want to measure this many number of digits in pi, but apparently on Pi Day, this is something that is sort of a tradition. Nerd alert! I'm actually getting into that too, right? March 14th. Anyway, so pi is the ratio between the circumference of a circle and its diameter. So 1 radian is the ratio between the arc length and the radius. So we can calculate the conversion from 1 radian to a degree and vice versa by knowing that pi is 180 degrees. Remember, circumference 2 pi, 1 revolution is 360 degrees. So 1/2 of that, which is a semicircle, is pi, 3.14, because that's equal to the diameter. So that's 180 degrees. So therefore, if you ever want to convert from degrees to radian or vice versa, just know this relationship that 180 degrees divided by 3.141529 is 57.3 degrees. Anything you need to remember is that number, 57.3. Cool. So let's take a look at a few examples here. I have someone here that is in neutral position, and we're going to be measuring horizontal abduction, adduction. So he goes from 0 degrees to 45 degrees of horizontal adduction. You guys know what the difference is between horizontal abduction and adduction. So the angular displacement obviously is positive 45 degrees, or 45 degrees of horizontal adduction. Or in radians, is 0.73 radians. Angular speed and angular velocity, the concept's still the same. You could calculate it the exact same way. The only difference now is you're looking at time. And angular speed is simply the scalar rate of angular motion. It's the magnitude of the change in angular motion over time. Whereas angular velocity, you have to include a direction. So if I gave you that same example where the person horizontally adducted at 45 degrees and did it in 1 second, his angular velocity is 45 degrees per second in horizontal adduction. So in this case, your direction, you depending on your coordinate system, is defined as, in the clinical planes of motion, adduction, adduction, flexion, extension, internal, external rotation. It depends on the coordinate system. But again, look at this. You'll notice that magnitude, in this case in degrees or radians, and direction, which could be adduction, adduction, internal, external rotation, or positive, negative, depending, again, on the coordinate system. All of that is still the same type of concept that we described or that we discussed in linear kinematics. So let's take knee. So this is knee extension. The person started roughly at 90 degrees or with the knee flex and decided to do an open chain extension. And this is the change in angular position. and roughly 86 degrees, right? 86 degrees of knee extension. This person did it in 2 seconds, so the angular velocity is 43 degrees per second in knee extension. And because we know the radius, that's the distance between the axis of rotation of the knee and just say the lateral malleolus, its linear velocity can be estimated as 0.375 meters per second. And I'll show you exactly how we measure that using the radius and this angular velocity. Now, what I just mentioned here is what's known as the tangential linear velocity, which is the linear velocity at that point that's tangent to that circle. And it can be calculated using this really simple equation here, where the tangential linear velocity, again, is a point on the rotating segment, is equal to the product of the angular velocity and the radius. And it's important to note that that angular velocity here, which is denoted here by omega, needs to be in radians per second. It's a dimensionless unit. Multiply that by r, radius, which is in units of length, so that would be in meters, you get meters per second. So we can convert from angular velocity, if we know the radius, and determine the linear velocity at that point in time. So let's take Tiger Woods here. Got Tiger Woods, who's going from the backswing. He is currently doing or swinging looks like a 9-iron. And we want to calculate the exit velocity of the ball, or the linear velocity of the ball at ball impact. And we can use that relationship between angular velocity and linear velocity given these known quantities. So omega here denotes angular velocity, and it is 33 radians per second. The distance between the axis of rotation of, let's just say his longitudinal axis of rotation, and the end of the iron is 1.2 meters, or 120 centimeters. You multiply 33 times 1.2, you get 40 meters per second. And so at ball impact, the ball takes off, assuming there's an elastic collision there, at plus 40 meters per second, depending on the coordinate system that we're using. So now you can begin to understand what influences linear velocity of, say, a golf swing. Think about all the athletic movements that you either play or that you've either performed or watch, whether it's a golf swing. I'm going to show you here about looking at a hitter, a bat swing, throwing a javelin, throwing a baseball, throwing a football. All that requires rotations, segmental rotations that equate to a certain linear speed or linear velocity at takeoff or at ball contact. So it's able to, and what's the point of many of this? Is in this case, we're looking at the golf swing. We're trying to launch that ball so that it stays up in the air as long as possible, so it travels as far as possible. Or if you're looking at a baseball or a football, you want to be able to throw that implement as fast as possible so that it can travel farther. And the only way we can do that is through these angular velocities of each individual body segment. So I'm going to talk about that in a sec here with kinematic sequence. So when we're talking about angular velocity and angular speed, very similar to what we did for linear speed and velocity, there's the average velocity or average angular velocity, but there's also the instantaneous velocity. And really that's what we're interested in, is we want to know what is the instantaneous velocity at ball contact or at release, ball release. Or we're interested in the peak angular velocity, and that is especially important when we're talking about the kinematic sequence. So let's take a look at bat speed, and I want you to give this a shot. If, for example, this batter here is swinging at a fastball, makes contact at an angular velocity of 3,000 degrees per second, and the distance between his axis of rotation, his longitudinal axis of rotation, and the sweet spot of the bat is 0.8 meters or 80 centimeters, what is the bat speed at ball impact? Give it a shot. Good. Should have gotten something close to either 93 or 94 miles per hour. So let me show you how to do the work here. Bat speed. And we are going to use the relationship between linear velocity and angular velocity. Now keep in mind, this is tangential linear velocity, okay? And we know that the relationship between angular velocity, which is the velocity in moving in a circle, as you know, is related to the linear velocity that is tangent to that circle. And that relationship is given by omega times the radius. That's angular velocity times the radius. So the question here is, what is the bat speed at ball impact, given that the angular velocity is 3,000 degrees per second, and the radius, which is the distance between the batter's long axis of rotation and the sweet spot of the bat. So 80 centimeters is actually 0.80 meters. The first thing that we need to do, we've got everything, we can easily plug this into our equation, but before you do so, you have to calculate or convert the 3,000 degrees per second into radians per second. So I am going to be using my calculator, where you're going to go 3,000 degrees per second, divide that by, because there's 1 radian for 557.3 degrees, so I'll take 3,000 and divide that by 57.3 degrees. Should give me roughly 52 radians per second. So now I've converted it, that is 52 radians per second times that by the radius, which is 0.80 meters times 0.80 meters. That should give me roughly 42 meters per second. Am I done? No, because I need to convert that to miles per hour. And I already gave you how many miles per hour. That's 2.23. So you should get roughly 94 miles per hour. All right, let me double check my math, make sure I got that. So that's 42 times 2.23. Yep, 94 miles per hour. And that's it. So now let's talk about the kinematic sequence. This is arguably one of my favorite topics to discuss, simply because I work a lot in baseball in terms of my research, whether it's with baseball hitters or baseball pitchers, where the kinematic sequence is an important aspect of their mechanics. So the kinematic sequence refers to the timing in peak angular velocity of each relevant segment or joint that's involved with the movement task. So take, for example, this baseball player. He is hitting a baseball off a tee, and the graph here on the right represents the angular velocities of the pelvis, trunk, and shoulder. And right now, don't focus too much on the magnitude of angular velocity, but I want you to concentrate on the timing in which each one of these peaks occur. In fact, if you look at this, the peak angular velocity that occurs first is the pelvis, followed by the trunk, followed by the shoulder. That represents what's known as a proximal to distal sequence in segmental rotations, which equates to a certain flow of energy through the kinetic chain, what we call mechanical power. So if a player is efficient at performing this kinematic sequence, specifically in the proximal to distal fashion, he potentially has the ability to maximize the energy to the throwing arm or through the swinging arm, so that by the time he makes ball contact or releases the ball, if we're talking about a pitcher or a quarterback here, he is able to maximize angular velocity and subsequently maximize the linear velocity, what they call exit speed, at contact. And typically what you see in terms of sequential timing, whether we're talking about a baseball pitcher or a baseball hitter, it goes from the legs up through the pelvis, up through the trunk, and through the arms. And if we look at a baseball pitcher, here is a spatial model, a three-dimensional spatial model of a baseball pitcher, and this specifically is the mechanical power of the various segments of the body. More specifically, it's the rate of energy transfer from one segment to the next. That equates to angular velocity, because mechanical power is actually calculated using angular velocity. So when the segment reaches or turns red, as shown here, that indicates that the angular velocity for that particular segment is peaking. And look at the flow. Look at the flow of energy, mechanical energy, through the kinetic chain, from the legs to the pelvis to the trunk, and ultimately to the throwing arm. that should equate to a proper kinematic sequence, specifically a proximal to distal kinematic sequence. And if we look at this player here, again, pelvis is represented here by the red curve, the trunk represented here by the purplish curve, elbow is represented by the green, and then the gray curve is the shoulder internal rotation. Notice here that the sequence throughout the pitch cycle, and let me show you the pitch cycle. This is the what's called maximum high, knee high, and then front foot contact is here, and then ball release. This right here represents the arm cocking and the arm accelerating phase. Look at the sequence. The sequence goes in a proximal to distal fashion. The only caveat for baseball pitching is that elbow extension angular velocity actually peaks just before the shoulder peaks in internal rotation. And what we believe is happening is that as the shoulder is internally rotating into ball release, the momentum that's generated from that motion itself passively extends the elbow, where it peaks just right before, we're talking a few milliseconds, right before the shoulder reaches its internal rotation velocity, its peak rotation velocity at ball release. This red line represents ball release. So again, that's just a few milliseconds. So this is what, for all intents and purposes, this is happening at the same time, where the person is, or the pitcher is internally rotating or peaks at internally rotating, as well as extending the elbow. That combination, along with what's happening, in the larger segments, in the larger proximal segments, equates to an angular velocity at the wrist and hand, and subsequently a maximum linear velocity of the ball at release. This right here is a summarized graph of, more specifically, the timing of these various segments, the kinematic sequence, in relation to what we find in a sample of 33 adult pitchers here. So you can see for this player, his pelvis angular velocity peaks before front foot contact, which is actually a good thing, followed by the trunk, followed by the elbow and shoulder. So this is pelvic rotation, trunk rotation velocity, elbow extension velocity, and shoulder internal rotation velocity, which should peak right around ball release. Okay, so now let's talk about angular acceleration. If you're familiar with linear acceleration, then angular acceleration should be pretty straightforward. The only difference now is we're looking at the change in magnitude and or direction of the angular velocity with respect to time, as shown by, or as calculated by, this equation here. So alpha is typically used to denote angular acceleration. Omega is used to represent angular velocity. The change in angular velocity over time gives us angular acceleration. Pretty straightforward, right? Now, to determine the direction of acceleration, it's actually the same thing that we do for linear kinematics. So now we're looking at angular motion. So if angular velocity, you're looking at angular velocity, look at that direction first. If it's slowing down, then the acceleration, or the direction of acceleration, is going to be opposite the direction of angular motion. If it's speeding up, then the direction is going to be in the same direction as angular motion. Let's look at an example. You got someone that's landing from a jump, doing a drop vertical jump, and as the person's landing, he wants to come to a complete stop, so he fires his hip extensors, his knee extensors, as well as his plantar flexors here. And if we just concentrate on the knee joint, we know that the knee is flexing, but it's not because the hamstrings are firing, right? It's because it's just the position that he's in, the ground reaction force, and the weight of his body is causing his knee to go into flexion. So to counter that, what does he need to do? He needs to fire his knee extensor. As he's flexing his knee, or as his knee is flexing because of the GRF and because of his weight, for example, in order to slow it down, he has to fire this knee extensor. So the act of slowing down, in this case, in knee flexion, the direction of acceleration would be in the opposite direction, which is knee extension. Think about what's happening here. Which muscles are firing? His knee extensors, right? His quadriceps, his knee rectus femoris, his VLATs, his VMOs, all eccentrically contract in order to slow down the rate of knee flexion as he's landing from a jump. So if you ever get confused in terms of direction of angular acceleration, just think about your anatomy. Think about which muscles are firing, either eccentrically or concentrically. If they're concentrically firing, then you know they're speeding up. right? They're causing it. Let's say, for example, he lands from jump and then it does another counter movement jump. That is concentric contraction there. So just think about your anatomy, then you'll know the direction of acceleration. Now, angular acceleration, the linear kinematics that is involved with angular acceleration, there's actually two. In angular velocity, we only talked about tangential linear velocity, but in angular acceleration, there's tangential linear acceleration as well as centripetal acceleration. The tangential linear acceleration is just the linear acceleration of a point on a rotating object, rotating segment in this case. And that is calculated off this nice little equation here, which is the change in tangential linear velocity over time. So you notice here that it is only going to change if the angular velocity changes, if the magnitude of the angular velocity changes. So again, that is the velocity vector that is directly tangent to the path of the object. Now, because the rotating object is all constantly changing directions, right? Your rotating is constantly changing direction. So therefore, there's also acceleration that's directed towards the center or towards the axis of rotation. We call that centripetal acceleration. You guys have felt centripetal forces when you're driving and you all of a sudden need to make a left turn or right turn, and you feel yourself leaning in the opposite direction, because that's according to Newton's first law. You know, you want to continue to go in that certain direction, but that force is drawing you closer or towards the center. We call that centripetal forces, and the acceleration associated with that is centripetal acceleration, and that is calculated using this nice little equation that is the tangential velocity squared over the radius, or angular velocity squared multiplied by r. So just by looking at this equation, which do you think would have more of an effect on centripetal acceleration, angular velocity or the radius? Good. Yes, angular velocity, because of the squared function, right? So if you square angular velocity, that would have more effect on centripetal acceleration. Now, if you see this here, as I mentioned earlier, you're a race car, and if you were to drive around in a racetrack in a circle constantly, you would feel centripetal acceleration that's directed towards the center of that racetrack, because you're constantly changing direction. And that centripetal acceleration is a function, as I mentioned earlier, of the square of the angular velocity as well as the radius, which is the distance away from that center of rotation.